Welcome to our NPTEL courses, Advanced Power Electronics and Control. We discuss more about the control and we will take out first the linear and nonlinear control applied in the power electronics, or how actually power electronics has to be actually utilized with the effective control. Generally what happen, why we require power electronics, I have several times talked about it, that you may have a raw power, that is something, that input voltage and frequency that is coming from the any sources, and the load will take a different kind of voltage or the frequency. So, for this reason we require a DC converter. It can be actually AC to AC converter, which can change the frequency, which can change the amplitude. It can be DC to DC, and it can be bidirectional, and not only the power flows through this point to this point, it can flow this point to this point also. So, all the possibilities will be there, and ultimately actually there will be a feed forward path, there will be a reference, and thereafter there will be a feedback, and from there will be a control strategy and that will be fit to the converter or inverter to give a desired output at the power level. So, we can brief in this statement in that way, that switching power converter must be suitably designed and controlled in order to supply voltage, current, frequency and the ranges needed for the load, and guarantees a required dynamics. So, what happen actually, dynamics means their load is not a static entity, it may change and it is totally the control of the on the consumers, but irrespective of the load change, and you should give a desired output voltage. Similarly, you can have a source change, that is practically possible in case of the renewable energy applications. There is a uncertainty of the wind, there is uncertainty of the solar irradiation, and thus this input power also changes, but you require a desired actually level of voltage and current to feed, otherwise you have to take different measures. Control designers for switching power electronics converter should know static and the dynamic behavior of the electronic power converter. That is very important to understand actually proper designing of the any converter. Switches are dumb unless it is fitted with the control, and we say that it is control, and the power electronics is just like a life and the body. A power electronics converter gets its life through the control. So, for this reason it is quite important aspect to learn how to control these converters. So, and how to design its elements for the intended operation modes, and thus a power electronics expert required to know a formidable amount of the control systems. So, designer must be an expert on the control techniques, especially in the non-linear ones, because once you are switching, your system is non-linear. The world is non-linear, but we actually, for the sake of simplification and modeling, we make it linear. We first see that how you can linearize, and we will see that problem of the linearization, then we shall go back to the actual nonlinear system, we shall try to solve the problem that arises not considering the nonlinearity. Because switching converters are nonlinears, a time variant discrete system. Generally nonlinear works is actually time invariant continuous analogous systems. Designer must be capable of analog or the digital implementations of derived modulation regulator and comparators. Now, issue is that actually world is going towards the digital converters, digital control, because previously there was a problem of the switching and problem of the sampling rates, and thus actually we try to solve in the analog domain. But gradually, due to the invent of the high speed processors and dedicated processors like FPGA, so these problems are actually now analog is basically phasing out gradually because of the uncertainty in nature. But we require to understand the analog working principle and the control of the analog circuits very well to mimic the same characteristics in the digital domain. Suitable control requires for not only with the satisfactory static dynamic performance, but also with a low sensitivity against load or the line disturbances or preferably the robustness of the system. Now, this is a typical control term, the robustness. It means that actually system will remain stable with the perturbations. So, it will not actually come out from the zone of stability. Example of the stable system is the pendulum. If you give a perturbation, it will come to the stable equilibrium point. Now, this is the dynamic. We have basically a dynamics of the system that is converter, and we may have a two kind of solutions. One is basically the state space representations, mostly this has been propagated by USA, and another is a fundamental concept of the transfer functions that was propagated mostly from the UK. And ultimately, we will have a set of differential equation, world is governed by the differential equations, and thus actually trend of solving is towards the state space representations, and gradually these transfer functions methods, because it works well in a linear system, there are many actually technique you will be aware of. Bode plot, we will touch upon the little bit about it, but mostly our discussions will be concentrated to the state space representations. That is the modern control technique. Now, let us take a buck converter that we are studying several times. You know, there are two mode of operation, one switch is on, another switch is off. So, one switch is on, so this is the part of the circuit and that is the x1 the state, and so input is U1, and generally, so you can write these equations U1 equal to Lx1 plus x2, where x dot equal to basically it is nothing but V equal to L plus Ri, and where x1 equal to C x2 dot plus x2 by R. So, similarly, when it is off state, we can rewrite the equation, there is no voltage source, ultimately power in the inductor will actually flow into the circuits, and assuming that diode is ideal. So, then actually this is the equations that will be governed. So, 0 equal to L dx dt plus x2, that is a voltage across the capacitor, and similarly you can rewrite this equation. So, you can see that how this actually this kind of matrix are available. This A matrix are same. So, you can combine for 0 to t on this matrix, and for t on to t off this matrix, and they require to be combined for the total time period, and that is said to be the averaging model, because one phenomena is existing for the time t on, another phenomena existing for the time t on to t, and in between they have to be coupled. So, we can say that supposing the power semiconductors are control ideal switch, this is our assumptions, 0 on state voltage drop, 0 off state current, and instantaneous commutations between the on state and off state. The time behavior of the circuit over period t can be represented by the general form of the state space model, that is basically x dot equal to Ax, that is called state space matrix, and this is basically the input variable matrix, that is B, and y equal to actually Cx plus Tu, where generally in case most of the cases you will find that current through the inductor and the voltage across the capacitor are taken as a state, because it is essentially you can equate V equal to L d I dt and C dV dt equal to I. So, thus they are the state of the system, where x is the state vector and x dot equal to dx dt, and u is the input vector and y is the output vector. A, B, C, D are respectively dynamics or the state, input, output, and the transmissions or the feed forward matrix. So, we can have a block diagram representation that has been covered in your typical control system book. Because of lack of time, we are actually not discussing those things. Students are advised to actually actually read about a state space from any control system book or any NPTEL lectures on the control system. Now, let us go into depth about the state space modeling. Since power semiconductors will be either conducting or blocking, a time dependent switching variable del t can be used to the desirable allowed the switch state of the each structures. So, del t equal to 1 for the on state and del t equal to 0 for the off state of the circuit. Then two sub interval must be considered for the interval 1, that is actually 0 to is actually t greater than 0 and less than del t 1 into t, which is basically 0 to t on, in other words, and where delta t equal to 1, and where delta 1 is the duty ratio between on state to off state, and again sub interval 2 from delta 1 t less than t and less than t, where del t equal to 0. So, this in this case here delta t will be 0 and in this case delta t will be 1, and accordingly we shall rewrite the state space equations. Here when actually switch is on, power was flowing from the source to load, so we got these equations, and another set of equation where delta t equal to 0. So, we require to combine these two equations. So, our foregoing equation can be combined to obtain the non-linear. Previously this was a linear equation. Unfortunately, there is a state change between these two, thus the system become non-linear. Obtain the non-linear time variant switching state space model of the switching converter. So, you just have this average model, rewrite it, actually you got a vector a 1 into del t and a 2 1 minus del t into x sim plus b del t plus b 2 1 minus del t into u. Similarly, for the output state for observable matrix basically C 1, similarly we can write, and thus it becomes a combined matrix where A s is given by A 1 into del t plus A 2 1 minus del t, and generally A 1 and A 2 are same most of the cases, and B s actually B 1 into del t, B 2 1 minus del t, and so on, and thus you have other also the matrices. Now, we wanted to have something called average state space model. Some phenomena we require to observe, and that is possible because it is switching. So, once we say that it is average, so we are not capturing any phenomena at the rate of the switching frequency. We will be capturing basically 1/10 of the switching frequency, and we will analyze the stability of the system. So, then we will say that it is a average model, essentially you are adding. So, suppose that the average value of x and denoted by the x bar are the new state variable, and considering that you know these are basically del 2 has a relations, that is 1 minus del 1, and moreover if A 1 into A 2 as an associative matrix basically equal to A 2 into A 1, the approximations can be actually made here. So, we can see that. So, if you rewrite these equations basically in terms of delta 1 and delta 2, ultimately you will get basically A equal to A 1 delta 1 plus A 2 delta 2 Similarly, these associations can happen, and if it is possible, then let us take a example, practical example, how this actually matrices can be used to analyze a particular circuit. Since we had talked about the buck converter, let us take a buck converter and consider that following design aspects. Consider a simplified circuitry of the buck converter, and we will assume that all the switches are ideal. And since shortage of the time, we cannot go beyond, otherwise then we gradually take a evaluate, and once we take the losses and what does happen to it. Anyway, for time being, we shall take out a buck boost converter. That is quite universal converter, because it can buck, it can boost both. And here switching is basically at 20 kilohertz, that is fixed, and this is basically 50 microsecond. With VDC max, this value, it may be a solar panel, it with voltage changes according to the irradiation, that is 28 volt, and VDC mean, this voltage can drop up to 22 volt, and we want that actually 24 output at the output voltage, and you have chosen from the design aspects that you have seen for the continuous conduction mode, that value of the Li is 400 microhenry and C equal to 2700 microfarad and R0 equal to 2 ohm. And we assume that this is in a continuous conduction mode, otherwise analysis will be tough, and we shall write this state space model and we should analyze its stability of this converter. Please see that this is a design problem. So, let us rewrite the equations for the differential equation governing the dynamics of the state space, that is current to the inductor and the voltage across the capacitor, that is essentially the output voltage. So, L di dt equal to VDC and C0 VDT equal to minus V0 by R. It changes its polarity, because for 0 to actually del T1, delta equal to 1, Q1 is on and diode 1 is off, and thus you get these matrices. So, you get actually matrices A1 as 0 0, and similarly in second case for the del 2 you will get another set of matrices which come little later. So, similarly you get actually L1 dual L equal to minus V0, and for this other interval for actually del 2, when actually Q1 is off and D1 is on. So, you get these two matrices. So, combine these two matrices. So, for this you get basically this matrix, and from this you get this matrix. Similarly, B1 is basically will be this matrix, and B2 will be your this matrix, and where U equal to VDC, and C1 C2 are there is no D. So, there is no link between input and output. If there is a link between the input and output, then only the D matrix comes, otherwise D matrix does not come, it generally 0. So, C matrix will have this kind of form. Now, let us actually see, you combine the switching of the state space and you add up with the 1 minus del T and of these two values, and then since actually we consider that the average value, that is x bar, and the new state variable considered to be the del T equal to 1 minus del 1, and also here you can see that A1 dot A2 is A2 dot A1, and the equation can be changed as discussed into the previous slide. So, you can add it up, ultimately overall equations become this. Students are requested to physically do that calculations. So, V0 by L equal to this delta 1 plus delta 2, that is A1, this is A2, thereafter this is B1, this is B2. So, similarly C1 and C2. So, this is the actually the x dot equal to x plus Bu total form. Once you get these equations, then we can find the roots of this polynomial. This is a very simple circuit, thus it is a 2 by 2 matrix only. So, basically you have to write lambda minus 1 and this will be lambda plus 1, and ultimately you have to find the roots of the Si minus A, and these roots of the polynomial will give you the characteristics of this circuit. Let us see that what happened. So, of course, there is a three of course, roots can be imaginary, roots can be actually complex conjugate, and roots can be real. So, see that what happened in three conditions. Since the delta max is the maximum absolute value of all the eigenvalues of A, the model proposed is valid switching frequency, and that verify actually lambda max t less than should be 1, as t less than 1 by lambda max, the value of t approximately verify the restrictions are that 1 by max, this value gives this actually Buck-Books converter, that, and this is actually you can calculate. So, ultimately these values actually will be less than the 2 millisecond. Therefore, the converter switching frequency must obey that Fs should be greater than the maximum value of actually mod of SASP, implying that switching frequency should be above 5 kilohertz. So, we are well above the 5 kilohertz, no problem. If it is with these values of the capacitor and the inductor, we require to have the switching frequency more than 5 kilohertz. Consequently, if it is less than 5 kilohertz, what will happen? Of course, there are many possibilities. First things you will find that it will be discontinuous, and thus when it is become discontinuous conduction mode, current does not flow and you cannot control the output voltage, control becomes a difficult task. Consequently, the buck-boost switching frequency and the inductor value and the capacitor values are chosen accordingly. So, you have, if you choose this actually 5 kilohertz, then we have to change the values of this capacitor and inductor, and we have to see that same eigenvalue, it may actually bring it. It is advisable basically this value should be around 2 to 5 times, at least 2 to 5 times less than the switching frequency. So, let us see. So, what now questions comes, one observation we got from the state space, that what should be the desirable frequency and whether you are well above it or not. Now, another way to actually analyze the state space, once you already got a state space, because it is a set of differential equation written in the matrix form, it is a very simple thing to do for many of us. So, what happen if you give some disturbance across the average value. So, you got an average value, and since we have actually assumed that these values to be constant over a period of time, because your switching frequency is quite high and your observation time may be actually at least 1/10 of that, and in that time you assume that actually things are constant, and there you basically give a change and see that what happens. Hence, the circuit often named average equivalence circuit. So, average equivalence circuit, it is something like that, if you got this kind of waveform, you may say that I got this much of average value, over it there is a imposition of a sine wave. We may say in a control system, this is the average value, over it there is a perturbation or disturbances. So, the average equivalence circuit of the buck-boost converters allow the determinations under small ripple and the slow variations. So, this phenomena, that is what I was saying, though this phenomena can capture the phenomena like under small ripples and the slow variations can be captured, and provided that those entities are happening at least 10 times slower than the switching frequency. The average equivalence circuit of the converter switching cells, actually it has been shown here. So, this is a modeling because it is a current source, thereafter you got an inductor, you just go back to the actual circuit, then only you can recall what changes what. So, this has been a current source and this diode has been made a voltage source. So, it will block the voltage and ultimately it will work like basically VDC plus output voltage, and this will be the output voltage of reverse polarity. Now, let us analyze it, that is a state space modeling and linear state space average model. We know that system is nonlinear, fine, but once we design a controller, design the linear controller is easier to do. And for this reason, we considered that, so actually within a small interval of time, we considered that system is in around its average value. So, we will linearize this circuit and or operate this circuit in and around its average value. Then we will say that it is a linearized state space average model. Okay. So, since the converter output Y must be regulated actuating on the duty cycle del T, the converter inputs U usually presents perturbation due to the load and the power supply variations. So, we shall consider that this has some constant value with a perturbation. The state variable are decomposed in a small AC perturbations denoted by delta, and the DC steady state quantity represented by the uppercase letters, and therefore, it can be splitted like that. So, is this average value will have a DC value, above it there is a perturbation. Similarly, Y will have a perturbation, that is you got 24 volt DC, that signify this, and with that you got a ripple that signify this, as simple as that. Similarly, in some instant of time your input voltage may be something, and with that you will assume that there is a perturbation. And similarly, there will be variations of delta 1 as well as the delta 2, these are the duty cycles of this converter. Now, let us combine, we have already combined A1 and A2, on state and off state, and we have combined, and now we will write basically the perturbed term, that is basically the disturbed term. Average terms are fine, we require to take the perturbed term only. So, that will be actually x delta dot. So, that will be A1 delta 1 plus A2 delta 2 into x plus B1 delta 1 plus B2 delta 2 into u, and thereafter you will have basically A1 delta 1 plus A2 delta 2 into this. Similarly, you will have this into delta. So, you will have so many terms, because basically you are subtracting both these things. Similarly, this is basically in a state, and similarly in Y delta you will have similar representations. We shall discuss about this state space model in our next class. Thank you for your attention.